we are going to start our discussion on network theorems. And which is also known as circuit theorems or circuit theory. So this is useful for solving a network. So these are useful for solving networks or circuits. So I will use the shorthand CKT for circuits. So what do we mean by solving a circuit? So we mean that if we are given a complicated circuit, very complicated circuit with a lot of impedances and sources. So let me try to draw a very complicated circuit for you. Let's see if it is complicated enough. Then let me take some sources. So I'm taking a current source which is denoted as this arrow. Then let me take a voltage source like this, and then maybe another voltage source, maybe another current source, another impedance, and one more. I hope it's complicated enough to understand our theories. Okay, we can name them as Z1, Z2, Z3, Z4, Z5, and so on. Like I can call it in general Zk. Now, solving this circuit means that we are given the impedances. So Zk in general, Z1, 2, 3, 4, etc. So these are given. We are also given the sources. That means voltage and current sources. So their values, like maybe this current is, maybe this is I5, let me call it this voltage, let me call it Vs, let me call this capital I5, let me call this as capital I1, this one as V, or okay, let me use capital V4, then this, what else, this is capital V3. So all these values, and also their directions if required, of course required. So everything is given. Now the task is to find the unknown currents in all the branches, like what is this current I4, small I4, this is equal to what? Or this current, if I call it IK, this is equal to what? Or maybe this current, which I call it as I2, this is equal to what? So all these currents, what are they? And also all the voltages, unknown voltages or voltage drops across all the branches. So for example, what is the voltage drop Vk between these two nodes? Or what is the voltage across this impedance what is the voltage across this impedance. All these unknowns we have to find out. So that's this task. And how do we do this? How to do? By obeying some constraints or equations. What are they? Like number one, we have KCL. So KCL says that sum of the currents coming into a node should be equal to 0. So that means they say if I consider this node, then this current, if I call it I1 plus this current, okay, this is going away, so that should be minus I2, and this current I3, their sum should be 0. That's KCL, and this should be true for all the nodes. Then KVL, what does it say? It says take any loop, maybe this loop, this one, and then the sum of potential drops summed over this loop, starting from say here to here, then here to here, then here to here, that should be 0. Because I start from one point and come back to the same point, so there should be no net potential change. Like here, there should be no net accumulation of charge in a node. So this is KCL, this is KVL. What else? Yeah, the third one is very obvious, and it's so obvious that we always never mention, but this is also there. This is that Vk should be Zk Ik across all Zk. So if this is Zk and the current flowing through it is Ik, then the potential across it should be Vk. So this is so obvious that we never mention, but this is also a constraint that we have to satisfy, that we have to obey to find all Vk and Ik. So if we can find a set of currents and set Ik and set of Vk's which obeys all these equations, KCL, KVL and this one, then we call that as the solution for this circuit. Or in other words, if I make this circuit with these impedances and these sources, these values of current sources and these values of voltage sources, then the current that will flow through this branch will be I4 as found by solving this set of equations. The current that will flow in this branch will be Ik as found by solving this branch. So this set of equations I mean. So that's what is solving a network. Next, what we are going to look at is our first network theorem, which is substitution theorem. What does it say? It says start with the network. Let me redraw the previous network which I had. Or maybe it's a bit modified because I don't remember the previous one exactly. Doesn't matter. I just want to draw a complicated circuit. That's what I want. Okay, so this is the previous circuit I have drawn. And now what I will do, I will draw this circuit, I will copy this circuit twice more. Okay, so maybe once here, so exactly identical circuit I will copy. Okay, I will not draw this branch right now because I will do something there. I'll do something funny, and let me draw it once again. I'm trying to draw it as quick as possible. Okay, so that's the same circuit, but once again I haven't drawn this particular branch. And any branch is fine. I will just I'm just choosing this branch to do something funny. Now what I will do, okay, before that I will name them as circuit 1, which is the original, or let me call it circuit 0, 0 for original. Then let me call it circuit, I'll call it circuit V, and this I will call as circuit C. Okay, what I will do this. Step number 1, first solve the original circuit, that is circuit 0 or circuit O for original. Okay, so first solve it. So if we do so, then we will get some values of voltages and currents, like maybe I will have let me rename them Z1, Z2, Z3, Z4, Z5. So and this is ZK. So this is Z4, Z5, Z1, Z2. This is Z3. This is not there. I'll do something there. Z4, Z1, Z5, Z3, Z2. Okay, and let me call this as V1, 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 same thing, current source I1, 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 what else, this one is I2, 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 and okay, this one plus minus, let me call it V2, V2, and V2. Identical circuit, everything same set of voltage sources, same set of impedances, and same set of current sources. So first I will solve this circuit. So after that we will have IK and VK for all branches in the original circuit. So maybe I will have something like this current equal to IK, this voltage from here to here VK, maybe here it's obviously I1, maybe here it's I4, etc, etc. So all this I will get by solving this. Okay, so I first solve it, and after that I know this. Now I will do this. In the circuit V, I will replace this impedance with a voltage source. Okay, circuit V, replace any ZK. Okay, this can be any branch. This could have been this branch or this branch or this branch, doesn't matter. I just have chosen this one. So this particular ZK, replace ZK with a voltage source VK such that the value of VK is equal to ZK times IK. What is ZK? ZK is the original impedance. And what is IK? IK is the current that was flowing in this branch in the original circuit, which I got by solving the original circuit. So I take the product of ZK and IK, and that I call as VK, and I replace this branch with this voltage source VK. And how should the plus minus terminals be here? So here in the original circuit, this side was at a higher potential than this side because current was flowing from here to here according to my chosen direction. So that was my reference direction. If so I will take this as plus and this as minus. Okay, so do this replacement. do this replacement or do this substitution, okay, then if we do so, substitution theorem says that the solution solution of circuit 0, original one, also is a solution for this modified one, circuit V. Okay, so that means if I take the same solution as in the original circuit here, so I take this current as IK, then what else? If this current was originally I4, I will take this also as I4. If this current was originally I2, I will take this as I2, and so on. So if I do so, and also the voltages, say if this voltage was V2, I will choose this voltage as V2. Similarly, if this is V3 here, I will take V3 here, etc. Then that set of, that means this set of IK, VK satisfies circuit V. So this new circuit has a solution which is same as the solution of this circuit. So I don't have to solve it again. Or in other words, I can also say that instead of solving this circuit, I can replace this branch with this voltage source and then solve this circuit, and the solution that I will obtain here should be same as this one. And this how we have done it. So we have came from here to here, from this circuit to this circuit by substituting with voltage source. So this branch is substituted with the voltage source. Now we can do another trick. Instead of substituting with a voltage source, we can substitute current source. So here I will take a current source, and what I will do, the value of this current source, okay, so this is another form of substitution theorem. So in this circuit C, so we are replacing or substituting ZK with a current source IK, this is IK, such that IK is equal to the IK which was the solution in the original circuit. This is capital and this is small IK. Okay. So the current that was originally flowing in the original circuit, I take that value for this current source. Okay, and what should be, or how should be the direction of this current source? So in the original circuit it was from left to right, so here also I will take it from left to right, same direction. Okay, from left to right. Let me draw the arrow once again, left to right. Okay, so again the substitution theorem says that the solution of circuit 0 is also a solution of circuit C. Okay, so C for current source replaced and V for, that's how I named it, and V for circuit voltage source substitution. Okay, so that's what substitution theorem says, that I can replace any impedance, any branch with a suitable voltage source so that the value of the voltage is equal to the voltage drop in the original circuit across this impedance, or I can replace this with a current source such that the value of this current source is same as the current that was in the original circuit, that was flowing in the original circuit. Then the solution of this circuit and this circuit, or this circuit and this circuit, they will be same. That's substitution theorem. Now let's briefly talk about the proof of this substitution theorem. So proof. Okay, so for that I will draw the original, and or maybe I use I will redraw the original and the substituted circuit, and I'll come back, or maybe I can just do it here, I think. Okay, so the proof. The proof goes as follows. Okay, so what is the claim? The claim is that a solution of circuit O original is also a solution of circuit V. Okay, and it's true also for circuit C. Let's look at this one first, then we'll look at the other one. It's very similar. Okay, so we're claiming that the solution of circuit O is a solution of circuit V. So what does that mean? This means it's same as says that the solution of circuit O also satisfies the constraints or equations in circuit V. So what are those equations? Number one, we already have discussed, we have three types of equations: KCL, KVL, and and this sort of constraints like ZK times IK is equal to VK. So for any branch, the potential drop across an impedance would be the product of the impedance and the current through that branch. That's obvious. So this is what we are claiming, that the solution of this circuit also satisfies the constraints in this circuit. Is it true? Does it satisfy the KCL? Does it satisfy KVL for all loops? Does it satisfy these constraints for all the impedances, all the elements? So let's check them one by one. KCL. Okay. So consider any node. Consider this node. So here in the original circuit we had this current, which is I4 plus this I2 plus I1 with appropriate signs, right, that you know, depending on whether it's coming in or out. So with appropriate signs, this I4, I2 and I5, their sum is equal to 0. Now if we take the same solution, that means I4 here, I2 here and I1 here, or so then their sum should again, definitely the sum was 0 here, and same thing, summed will be 0 here, so that means KCL is satisfied in this node. And similarly, consider any other node, these currents flowing in this original circuit are same as the currents flowing in the new circuit. So if KCL is satisfied here, definitely KCL is satisfied here. So KCL is satisfied. No doubt about it. It's obvious. What about the KVL? Let's check the loops. Okay, so in this branch the voltage was say this voltage Z4 times, so this if this was, say, I call it V4, small v4 across this Z4, okay, V4, so I take the same value V4 here, and similarly if this was V2, I take V2, and so on. Okay, so this will be small v2 according to my notation. Okay, so then that means if I take the sum of this voltage plus this voltage plus this voltage by KVL here, it's 0. So definitely if I check KVL here, so this voltage plus this voltage plus this voltage, which is same as this plus this plus this, is again 0. So definitely KVL is satisfied. Okay, you may consider this particular loop, because you might doubt that in this particular loop, one branch is actually replaced. So is this going to cause a problem, because this branch is not same as this branch? But anyway, we have replaced it in such a way that the voltage drop across it in the original circuit is same as the voltage of this voltage source. So that means this voltage and this voltage they are same. So definitely if these three voltages were summing up to 0 here, then the sum of this plus this voltage is again 0. So KVL is also satisfied here. So no doubt KVL is satisfied. Now this one, ZKI. Okay, so anyway, see, no impedance is changed. No impedance is changed, and no from here to here. So here I had Z5, here also I have Z5. This current was I1, this is also I1, and I'm taking the same voltage. So definitely if I had here, if I call this as V5, and if I had V5 equals Z5 times this current capital I1, definitely I will have the same thing, V5 equal to this Z5 I1. So if that was true, here, then definitely it is true here. Once again, if this equation was true in the original circuit, then definitely it's true in the new circuit. So definitely that means the same solution also is applicable here. Okay. You may doubt at this point, because in this branch the impedance is changed. Okay, so in this branch ZK is gone and the new source has come. So here we do not have to check ZK equal to IKVK, because there is no ZK here. So that constraint is not available here. So you don't have to even check it. So this is true, because that constraint is not at all there, which we have to check, right? So that's true. So for circuit, so we see that all the constraints are satisfied. If so, that means this solution is also applicable in this circuit. Now similarly for circuit C, once again you can verify that KCL definitely will be true, because I have same set of currents that I have chosen as the solution. So that must satisfy KCL, if that was satisfying KCL in the original circuit. Similarly, KVL will also be true if KVL was true in the original circuit. And finally, ZK, IK equal to VK should also be true, because no Z is changed between these two circuits. And this particular branch doesn't have any Z, so I doesn't have any constraint to obey. So that is the proof. So that proves that the solution here is also applicable here and is also applicable here. In other words, if I replace any branch with a suitable voltage source or with a suitable current source, and instead of solving this circuit, if I solve this circuit or this circuit, the solution that I will have is same as the solution here. So instead of solving this one, I can solve this one if this is easier to solve. Or instead of solving this one, I can solve this one if this is easier to solve. So that's substitution theorem. Okay, thanks, cool.